video I want to talk about IIR types of responses, particularly in the discrete time domain, which is often where we begin to start asking about IIR responses. When we're in the continuous time domain, IIR responses show up everywhere. We just get used to them, and we have to be very specific to get FIR type looking responses. And that's actually going to be kind of important, that the physical world tends to give you much more IIR type of responses, which is one of the things that you'll often want to think about using IIR systems to work with. But when I'm looking at it from a discrete time perspective, FIR filters are very, very straightforward to work with. And so the question starts to become, well, why am I going to use an IIR computation? And you might say, well, it has something to do with the physical world. Okay, that's nice. And then you might say, well, it has fewer taps for a given function. Okay, maybe, and so maybe something there. But I think it comes down to understanding a little more of what's going on with an IIR model and the richness that's going on there. Now, remember, very simple sort of thing, right? If I want to look at a derivative, say of some function z, in time domain, you might remember sort of the original the limit definition is z minus z of a time step, and that time step goes as small as possible, goes to infinitesimally small. Well, in a discrete time space, infinitesimally small is basically the next time step. You basically have gone from a continuous time structure to a discrete time structure and hoping you're okay. And many times you are, and sometimes you're not. But here we're going to talk about it being okay. And so now we have this particular form to look at. Now there's a couple other ways to write derivatives and second order derivatives and so forth. But just kind of work with this approach for a second. And what I'm getting in FIRs is that I can definitely get these differences, right? I can definitely get sums of derivatives. I can get a sum of one derivative, sum of another derivative. I can work with these various derivatives in higher order structure, and I'm adding them up. So it's very much of, okay, I know about Calc 1, and I can kind of build these things up and build up responses that have that kind of intuition to them. And in fact, you'll often see lots of things that look like something looks like an averaging integral or an averaging filter or a derivative filter. And you can then say, okay, what is that z transformation? What is the h of z? What is the frequency response? And it's a very straightforward approach. And there's some beautiful things you can do with this. And yet we know that we get into conversations of differential equations, and we can build difference equations around that. But differential equations have a very different perspective to it. There's a derivative plus that term equals to something in time. Well, that would then give me a question of y sub n equals y sub n minus 1 plus something of y sub n over here. So my y sub n minus 1 actually has to where I got from my previous calculation, not just my inputs, has an effect on the system. And so there's an iteration that's going on, very typical of sort of these sort of typical dynamical equations and state kinds of approaches. So I get something here also for y of n, and notice I can then take these two terms. I get 1 minus a t sample, so something close to 1. And 1's a very important term here. How close it gets to 1 there, and then probably some gain term on x, and you probably would gain that up. So it's important to think about that an FIR system is really about derivatives and integrals. IIR systems really start to bring out at least an approximation of what you get for ordinary differential equations. In fact, there's a whole field talking about difference equations, and typically in difference equations, you're taking sort of a differential equation mindset. You're taking these sort of more sort of richer IIR perspectives in it. And to get a sense of what you might see out of this, you're going to get a y of n equals a of n plus x. So for straightforward IIR equation set. And I want to look at its impulse response. So del x of n is just 1 at n equals 0 and then 0 everywhere else. Now, an interesting thing, if I were to look at this, I could actually say, what is the z transform for this? And that z transform turns out to be down here. Now, you may actually realize and may have seen somewhere that, in fact, the z transform for this actually gives me something in time that gives me sort of something that happens at a unit step function multiplied by that a changing to a power sub n, which is actually something you would see solving this equation. In fact, if you look at for a equals 5, an interesting thing happens. It starts off at 1, the next one's a half, a quarter, and it just starts dropping down. And so it's a very it's a straightforward approach. In fact, it's a nice thing that just generates, factors of 2 for you. If a is 0.9, what you notice is you get 1, 0.9, and drop, and you get this sort of dropping down over time. We get used to looking at this, and in fact, it almost feels like an exponential. And if you think about where this came from, the original first-order differential equation, I would expect something that would step up and then have an exponential drop over time. And we talk about a time constant and related things. And this is exactly what you see here. It's or at least an approximation thereof. Okay, so it feels very, very similar to it. Further, interesting thing happens if a is 1.1. It means I start off at 1, 1.1, 1.2, and it feels a lot like, oh yeah, I'm getting like yearly compound interest. It just keeps growing and growing and growing. And it goes up rather quickly. We can talk about a time constant again here. And so what you start to see is something that starts to feel more like differential equations. It has the richness of differential equations. And we shouldn't be surprised that when we're working with real signals that come from the real world or being used in the real world, we're going to have a similar issue.